This is lesson 1.5, Looks Can Be Deceiving, using proportions to solve problems. So the learning goals in this lesson you're going to address are to solve proportions using the scaling model. That's scaling up and scaling down. We've talked a whole lot about that. Solve proportions using the unit rate method, so meaning scale down to that unit rate, and then that makes it easier to look at um, things with larger values. And then solving proportions using the means and extremes method. And basically, we will break that down, and essentially it is cross multiplication. So some of you are familiar with that, so it should be pretty easy for you. The key terms that you will need to update are variable, means and extremes, solve a proportion, and inverse operations. So let's go ahead and get started. Have you ever seen a shark up close? Perhaps you have seen sharks at an aquarium or on the internet. Would you say that sharks generally look scary? Well, looks can be deceiving. If you encountered a basking shark, you might be startled, but there's nothing to fear. These mighty beasts actually swim around with their mouths wide open looking quite intimidating, but actually they're just feeding on plankton. Unfortunately, these sharks are on the endangered list in the North Atlantic Ocean. Have you ever wondered how scientists keep track of endangered species populations? How would you track endangered species? Well, we're going to get into some proportional reasoning to, in fact, answer those kinds of questions. So let's go ahead and get started. Problem 1, does that shark have its tag? Because it is impossible to count each individual animal, marine biologists use a method called capture-recapture method to estimate the population of certain sea creatures. Biologists are interested in effectively managing populations to ensure the long-term survival of endangered species. In certain areas of the world, biologists randomly catch and tag a given number of sharks. After a good period of time, such as a month, they recapture a second sample of sharks and count the total number of sharks as well as the number of recaptured tagged sharks. Then the biologists use proportions to estimate the population of sharks living in a certain area. So biologists can set up a proportion to estimate the total number of sharks in an area. So in this proportion, they set up using the original number of tagged sharks over the total number of sharks in an area. So we would highlight what's important to notice about this is the total number of sharks in an area and then the number of sharks caught in a second sample. So that means that is the total of what we're talking about in each instance. So the total number of sharks in an area, using an estimate, you would say the total number of sharks, and then we have the original number of tagged sharks in the numerator. And again, over here in the numerator, we have we have the number of recaptured tagged sharks. So both numerators are talking about tagged sharks. Both denominators are using total number of sharks. So when setting up a proportion, it is very important to keep those things in mind because you have to match up your units. You wouldn't want to put a total number of sharks with the number of recaptured tagged sharks. Like you have to set those up and put those in the appropriate places or your proportion won't be equivalent in the end. Although capturing the sharks once is necessary for tagging, it is not necessary to recapture the sharks each time. At times, the tags can be observed through binoculars from a boat or at shore. Biologists originally caught and tagged 24 sharks off the coast of Cape Cod, Massachusetts, and then released them back into the bay. The next month, they caught 80 sharks with 8 of the sharks already tagged. To estimate the shark population off the Cape Cod coast, biologists set up the following proportion. So in the denominator, we have, again, total sharks. We don't know the total number of sharks in the area. That's what we're trying to find. But we do know that 24 were tagged initially. So of the whole shark population, 24 were tagged initially. We don't know the total shark population, but we do know that we had 80 total sharks to begin with, and 8 were recaptured tagged sharks. So to reiterate one more time, these were the sharks that were recaptured. So remember how they tagged a bunch of sharks and then they went back out and they recaptured sharks? Well, this is the total number of sharks that were caught in the sample, meaning some were tagged and some were not. The ones that were tagged when recaptured were 8. We know that we tagged 24 sharks to begin with, and we do not know the total shark population. That's what we're trying to predict based on this proportional reasoning. So notice the P in the proportion. The P is a variable. A variable is a letter or symbol used to represent a number. In the proportion given, let P represent the total shark population off the coast of Cape Cod. So you should know what a variable is at this point in this class. A proportion can be written several ways. Think about equivalent fractions using the same 4 numbers. You can rearrange the numbers in equivalent fraction statements to make more equivalent fraction statements. So I'm going to try to explain this as easily as possible. In equation 1, we have 2 over 3, and then we have 4 over 6. We know that those are equivalent fractions. Below, all we did was rearrange the numbers, but they are saying the same thing. Instead of 2 and 4 being together in the numerator position, we have 2 and 4 together over top of each other in a numerator-denominator position. What's key about this is that you should be able to see that 2 over 3, those need to be together, 2 and 4 need to be together, 4 and 6 need to be together, and 6 and 3 need to be together. So let's check equation 2 and make sure that that's actually accurate. We have 2 and 4 together here. Those are our numerators in equation 1. We have 2 and 3 together here. Those are our numerator-denominator combo in equation 1. We have 3 and 6 together. Those represent our denominators in equation 1. And then we have 6 and 4 that are together, and those represent the numerator-denominator combination. As long as you can say that about every number in each of the different ways you write a proportion, then those proportions are equivalent. So let's check equation 3 and see if all of our numbers are lined up appropriately. So we have 2 and 3 together here, which represent the numerator-denominator combination in equation 1. Those need to be together. Remember, they either have to be together in a numerator position, together in a denominator position, or on top of each other. So 3 and 6 are together here, which represent our denominators in that first equation, so that works. 4 and 6 are together because they are on top of each other as a numerator-denominator combination in equation 1, and then 2 and 4 are together here, which they represent our numerators in that first equation. So each equation 1, 2, and 3, they are all equivalent, and they all represent the same information. So you could do the same thing in example 2. We have 15 and 21 together as a numerator-denominator combination. 15 and 21 are both in numerator position here, and 15 and 21 are both in denominator position there. We have 7 and 21 representing our denominators in equation 1. 7 and 21 are a numerator-denominator combination on top of each other in equation 2, and they are a numerator-denominator combination in problem 3. We also have 5 and 7, which are a numerator-denominator combination in equation 1. They are denominators in equation 2, and they are numerators in equation 3. So each set you should be able to do that with, or your proportions are not proportionate. So let's look at the problem. It says, in each example, use arrows to show how the numbers were rearranged from the first equation to the second, the first equation to the third. So based on my explanation, you should be able to do that on your own at this point. Then it says, write 3 more different proportions you could use to determine the total shark population off the coast of Cape Cod. So I'm going to rewrite those for you. I'm going to give you a second to solve it, and then I want you to come back and check yourself. So here's that information for you. We had 24 over P equaling 8 over 80. I want you to try this on your own and then come back. So in this problem, these are three different proportions that are proportionate to this original proportion. So again, we have 80 and 8 that need to be together because here they're listed on top of each other. We need 8 and 24 together because they're together on the top. They both represent tag sharks. We need P and 80 together because they're both totals. And we need 24 and P together because this is the number of tag sharks initially for that total shark population from, the very beginning. So let's make sure that these work. 8 and 24 are together here. 8 and 80 are together here. 80 and P are together here. And 24 and P are together here. That works. 80 and 80 and 8. 80 and P. P and 24. 24 and 8. We have 24 and 8 here. We have 24 and P. We have P and 80. And we have 80 and 8. So all three of those work. You have to do this every time. Again, I feel like I've said it a lot, but it's so very important. You have to go through that process each time to make sure that you have the units lined up and then those things that are written in the problem lined up as well. Estimate the total shark population using any of the proportions. So I want you to choose one of the proportions and I want you to try to solve for the total shark population. I chose this proportion because it makes the most sense to me. I can see that 8 times 10 would give me 80. So if I did 24 times 10, that's going to give me my P. So P is going to be 24 times 10, which 24 times 10 gives me 240. Now, you could have used different proportions and solved it and still gotten that same answer of 240. But just as number 4 asks, did any of the other proportions seem more efficient than others? This one seemed the most efficient to me because I could see that if I multiplied my denominator by 8 or by 10, I would get my 80, which is what I needed. So when you write those proportions in several different ways, you want to think about which one would be the easiest for me to solve, and that's the proportion you want to use. All right, so let's try our hand at writing our own proportion. Number 5 says, wildlife biologists tag deer in wildlife refuges. They originally tagged 240 deer, that's important, we want to underline it, and released them back into the refuge. The next month, they observed 180 deer, of which 30 of the deer were tagged. Approximately how many deer are in the refuge? Write a proportion and solve or show your work to determine your answer. So let's go ahead and start by setting it up. We have 3 numbers we're going to use, and then we need to choose a variable to represent our 4th term. So we know that there are 240 total tagged released back into the wild. So these are tagged deer. Then it says 180 deer, of which 30 were tagged. Because it says tagged, we need to put the 30 with the other number that represents tagged deer. So initially 240 were tagged, 30 that they, in their second sample, they went back out and they captured more, 30 of those were tagged. So because it says 180 deer, of which 30, those two numbers go together. So for that reason, I'm going to put it 180 down at the bottom as a total. Therefore, my X, we don't know the total out of that initial population 240 were tagged, but we don't know how many total were out there that they're talking about. So hopefully you're getting that tagged needs to go with tags. That's how I know that those need to go in the numerator together. These two were written in the problem together, so 180 of them, 30 of them were tagged. That's why I put those two on top of each other. And then our unknown is this x over here. In order to solve this problem, you can look from our second fraction to the first, because I can see that we have 30 here and 240 here, and I know that 30 times 8 gives me 240. Therefore, I have to do 180 times 8 to get my unknown. 180 times 8 gives me 1,440 total deer. So then again, we're using our scaling up method. You could have also scaled down and said, well, what did I divide 240 by to get 30? Well, the term is still 8. It's just more difficult to figure out, well, some number divided by 8 gives me 180, when it's much easier to scale up and say, you know, these terms multiplied by 8 gives us these terms. So it all depends on where your variable or your unknown sits within the proportion. A proportion in the form A over B equals C over D can be written in many different ways. This essentially is saying the same things that we talked about when we rearranged all those numbers and we had to figure out which numbers went together based on numerators and denominators and or numerator-denominator combinations. These are just variables that represent those different things. Show how the variables were rearranged from the proportion in the if statement, the two proportions in the then statements to maintain equality. So write all the different ways you can rewrite the proportion A over B equals C over D. Well, the first thing you need to think about is A needs to stay with C, A needs to stay with B. From there, C needs to stay with D, C needs to stay with A. And then from there, B needs to stay with D, and B needs to stay with A. So because of that, you can write like this. We have A and B staying together, but A also needs to be with C, so therefore C needs to go in the denominator position. B needs to stay with D, so therefore D needs to stay in that denominator position. Another one we could write would be starting with C up here and A over here. Again, C needs to stay with D, so D has to be down here. And then A needs to stay with B, so B should be down here. We could also write, starting with D, we could have D over B, and then C over A. Again, A and C are together, which they are here. A and B are together, which they are there. D and C here, and D and B here. We could also write D over C, and then B over A. So you should be coming to the conclusion that, yes, we can write these things several different ways. And again, when you write them out all the different ways, you want to stop and go back and think about, well, which one of these proportions makes sense for the problem? Which one's the easiest one for me to solve? And that's the one that you want to choose. All right, problem 2, quality control. The Ready Steady Battery Company tests batteries as they come through the assembly line and then uses a proportion to predict how many of its total production might be defective. On Friday, the quality controller tested every 10th battery and found that of the 320 batteries tested, 8 were defective. If the company shipped a total of 3,200 batteries, how many might be defective? Instead of actually solving this problem just yet, if you want to go ahead and try it out, you can. But before we do that, we're going to check out some different people's methods. So John David said that 8 effective batteries of 320 equal D defective batteries over 3,200 batteries. What he did was he knew that 320 times 10 gave him that 3,200, and then if he did 8 times 10, it would give him the D, which is that 80. So he thought 80 batteries might be defective. Matthew, instead, he said 8 defective batteries. He wrote a ratio, 8 defective batteries to 320 total batteries, and then D defective batteries to 3,200 total batteries. Again, he multiplied by 10 because he knew that 320 up here multiplied by 10 would give me 3,200 total batteries. And then 8 times 10 here would give me the total number of defective batteries. About 80 batteries will probably be defective, is what he came up with. So how are Matthew's and John David's methods similar? I want you to think about it, jot something down, and then come back and check yourself. So hopefully you came up with that both Matthew and John used the scaling up method, and they scaled up by 10 to figure out the total number of defective batteries altogether. So then we have Donald, which used a different strategy. I want you to take a look at what he wrote and then try to figure out what his strategy was. So at this point, we can see that he scaled down and then scaled back up, but try to think of a different way to describe what he's actually doing in this problem. So I hope you extended what you know about scaling down to see that he actually found that unit rate right here. We have 1 battery to 40 total batteries, which means that that's a unit rate. So he scaled down, found the unit rate, and then he scaled back up. Let's take a look at Natalie's. When I write Donald's ratios using colons like Matthew, I noticed something about proportions. So she looked at Donald's solution, and then she looked at the cross multiplication method. So the 2 middle numbers have the same product as the 2 outside numbers, so I can solve any proportion by setting these 2 products equal to each other. So go ahead and check yourself. Donald's solution, you have 8 times 40, which is 320, and 320 times 1, which is 320. You have 8 for Matthew's. We have 8 times 3,200, which is 25,600, and then 320 times 80 is 25,600. Okay, so number 4 says, try the various proportion solving methods on these proportions and determine the unknown value. Explain which method you use. So I'm going to let you use your own methods here and try and figure out the variable in each case, and then I want you to come back and check yourself. So hopefully you got those right. Natalie noticed a relationship between the means and extremes method. In a proportion that is written A colon B equals C colon D, the product of the 2 values in the middle, the means, equals the product of the 2 values on the outsides, extremes. So as you can see, they have listed here the difference between the means. Means is BC, so starting from the denominator up to the numerator. Extremes are starting from the numerator and going down to the denominator. Whereas if they're written in this form, the 2 on the inside are the means, the 2 on the outsides are the extremes. So to solve a proportion using this method, first identify the means and extremes, then set the product of the means equal to the product of the extremes and solve for the unknown quantity. To solve a proportion means to determine all the values of the variables that make the proportion true. So this should be familiar to you because it is exactly like cross multiplication. So in general, proportion can be written in 2 ways, using colons or setting 2 ratios equal to each other, as given here. You can write 4 different equations using means and extremes. Analyze each equation. Why are these equations all true? Explain your reasoning. So you should notice that both sides of the equation are equal because 7 times 6 is 42 divided by 14 is 3. So 3 equals 3. 7 times 6 divided by 3 is 14. 14 equals 14. 3 times 4, or 3 times 14 divided by 7 equals 6. And then 3 times 14 divided by 6 equals 7. So when both sides of your equation are equal, then they are true. Compare these equations to the equation showing the product of the means equal to the product of the extremes. How is the balance of the equation maintained in each? So go ahead and check yourself, and then we're going to move on. Why is it important to maintain balance in equations? I want you to think about that. We've talked a whole lot about equations and inequalities, but you know this problem specifically talking about equations. I want you to think about it and then come back and check yourself. So both sides have to represent the same value, so we must keep equations balanced in order to keep the equations true. In the proportion A over B equals C over D, you can multiply both sides by B to isolate the variable A. So notice we brought this out here, multiplied by B. If we do it to this side, we have to do it to the other side of the equal sign. We talked a whole lot about that. And basically what you're doing is performing inverse operations, which we've also talked a whole lot about. So in order to undo division, you're going to multiply. In order to undo multiplication, you're going to divide. In order to undo addition, you're going to subtract. In order to undo subtraction, you're just going to simply add. Another strategy to isolate the variables A is to multiply the means and extremes and then isolate the variable by performing an inverse operations. Basically, you should know how to do that. So you're saying C times B equals A times D. So that's what this is. And then you're dividing both sides by D. So it's the same thing as having a coefficient next to a variable that you divide by, which I showed you in previous slides on how to solve using that cross multiplication method. So it says describe each step shown. Step 1 shows that the products of the means and extremes are equal. The goal is to isolate the variable A, so both sides were divided by D in step 2, and the proportion was simplified in step 3. So that you should have had something along those lines written for number 7. Rewrite the proportion A over B equals C over D to isolate each of the other variables B, C, and D. Explain the strategies you use to isolate each variable. Well, if we're given A over B equals C over D, if we wanted, instead of isolating A, we wanted to isolate B, we're going to start out with the same strategy for both. AD equals BC, and then simply we're going to divide by the variable that is next to the one that we would like to isolate. So if we wanted to isolate B, we're going to divide by C. So AD over C equals B. Go ahead and try to isolate the variable C and then D and then check yourself. And there are your answers. Let's go ahead and move on. All right, problem 3. The school store sells computer games for practicing mathematics skills. The table shows how many of each game were sold last year. How many total games were sold last year? Well, you simply add all these numbers up. So 120 and 80 is 200 plus 50 gives me 250 plus 150 gives me a total of 400 games last year. The store would like to order a total of 1,000 games this year. About how many of each game should the store order? So what you're going to have to do is set up a proportion for each. So we know we have a total of 400 now, so we're going to put the 1,000 in the denominator position, which represents a total as well. And then you're going to put each of these numbers in the numerator one at a time and then solve for the missing term. I'm going to do the first one with you so that you get the idea, and then I'm going to have you do the rest on your own. Well, if we use the cross multiplication method here, we would do 1,000 times 120, and that's going to equal 400x. 1,000 times 120 is going to give me 120,000, and if we divide by 400 to isolate that variable, that gives me a value of 300 fast fact games. I want you to go ahead and try figuring out the rest of those and then come back and check yourself. Okay, so hopefully you checked yourself and you got the right answers. I'm going to let you at this point go ahead and work the rest of the problems in problem 3, and then I'm going to provide an answer key for you in class for you to check yourselves, and then you can